I want to talk about productivity today. Developer productivity, and especially the increasing focus on improving and trying to measure developer productivity. So where are we? So if you look up developer productivity, uh, you on Google, you'll get like a bunch of results about a lot of these products out there that are sort of starting to be called software engineering intelligence platforms. Right. So there's a bunch of these things. They collect data from your Git, from your CI/CD pipelines, from your project management tooling like Jira, and then they visualize all these a suite of metrics in a dashboard. Then hopefully people take intelligent decisions about how to improve your developer productivity. And there's also a bunch of competing frameworks, almost philosophies of how do we even define developer productivity? What are the right measures to use? One of them recently was from a management consultancy, and then there was a huge flame war online about whether individual developer productivity can be measured or not. Are you guys familiar with that? Some of you, yeah. I got like I whipped out my popcorn when Dave Farley published his YouTube video to rebut some of that stuff. Okay, the environment in which all of this is happening, of course, is companies are exceedingly talking about operational efficiency. So there's a cost pressure. So there's a huge demand for people to solve for developer productivity. So just another show of hands, how many of you at your companies have started adopting some of these tooling or thinking about adopting some of these tooling? 1, 2, 3, 4. Right, okay, so it's 6 maybe. So I don't know if you all work at the same place, but these things are on the uptrend, and the question becomes, okay, where do we go from here? Like, what are the right tools to choose? What are the right frameworks to subscribe to? What are the right metrics or measures? And what do we do once we have those measures? So before we can figure out where we want to go next, maybe it's good to look at where we've been before. So I'd just like to take a little bit of time to go backwards in history and look at what's been tried before by us software engineering people, other people, what has worked, and what are the lessons we can take from history. So there's these many flavors of developer productivity solutions out there, and we need to choose one. And almost all of them adopt or subscribe to the SPACE framework, which was published by Microsoft researchers and others in 2021. And this basically says that there's no one magical measure. You want to have multiple balancing measures across a few dimensions, and they suggest these 5 dimensions. SPACE framework itself builds on top of the research done by the DevOps research and assessment group. Some of the authors are common as well. So these are the famous 4 key metrics. They were published in 2017. And these are basically the foundation of the best known way we have of measuring developer performance or software engineering performance or outcomes. They also published a ranking of elite, high, medium, and this was published in page 19 of their award-winning book, Accelerate. And a fun fact about Accelerate is that that's easy to miss for readers, is that there are actually 240 other pages in the book that are quite good too. And DORA, of course, is an attempt to measure DevOps impact and adoption. Now, DevOps happened somewhere in 2008, 2009, when software delivery teams that had adopted Agile were moving too fast, and operational and IT teams could not support how many deployments they wanted to do. So they went looking for a solution, and from DevOps was born. And one of the first recorded conferences for DevOps was something called Agile Infrastructure. So that brings us to the mother movement, where in 2001, 17 wise men went on a ski trip up a mountain. I don't know if you know the story, but it's worth reading up. And they came down the mountain with this manifesto. They actually went on a ski holiday. So I'm not being weird. That's actually how they wrote this. So, and this was the new methodology for people to build software as part of teams that were solving for a lot of dysfunction that existed at the time. And they were confident this methodology worked because they had been practicing it for a while. And one of the most famous of these methodologies is extreme programming, which Kent Beck and others developed somewhere in 1995. Let's see if there's like an underlying pattern or principle here that we can identify that can help guide our future decisions of, okay, how do we think about developer productivity and how do we shape those initiatives? So I'll give you guys a clue and want you to put your detective hats on. And does anybody want to volunteer what you see as a common pattern in these three ideas? Okay, go ahead. Oh, yeah, thank you very much. Loops. So feedback loops. So all of these ideas encourage us to think in feedback loops and optimize for feedback loops. So it stands to reason when we think about productivity, are we picking a framework or tool that helps us think in feedback loops, helps consequences flow to where decisions are made? And feedback loops are also foundational to systems thinking. So for me, this is an attempt that we've been making about applying systems thinking to software engineering teams and organizations. So we're at XP, and now we'll take a leap here and see what we've learned from other sort of industries. And also in the 90s, in 1990, the researchers at MIT published a book called Lean, the Machine That Changed the World. Now, this is when the West realized that just why they could not compete with Japanese manufacturing for productivity, for cost, quality, and speed, especially Toyota. Now, a lot of lean principles have made their way into Agile and DevOps and DORA. WIP limits, small batch sizes, eliminating waste. Lean itself is, and there's this book by some of the founders of the Agile Alliance as well. Lean itself is westernized Toyota production systems, or TPS. Interesting thing about TPS, it was also a system of success in a downturn, in a cost-conscious market where things were really not going well. Now, TPS adopted and evolved alongside with something called total quality management, and total quality management had a lot of contributors, but probably none as significant as Edward Deming's. Now, Deming's, by all accounts, I never met him, was a brilliant man. He was a statistician, he was a physicist, he was a management consultant. And he is largely credited with transforming Japanese manufacturing in the 50s and 60s to the powerhouse that it became and maybe is. And that's not always a given, because Russell Akoff, another system thinker, tells a story that drives home the point. He said there's a town in Japan that named themselves USA. And they named themselves USA just so that they could print on the back of their subpa manufacturing, made in USA, made in USA. Because made in Japan didn't mean much. So, and now the award for quality in Japan is named after Deming's. But for Deming's, quality is not just about quality. Quality is a leverage point to improve the system. So you improve quality, you reduce costs, you improve productivity, and then there's a virtuous cycle. So for Deming's, the total in total quality management mattered more than the quality management. It's about the whole. And to give Deming credit, he was talking about this in the 50s. And it's only in 2017 when Accelerate was published, we as an industry sort of had consensus that speed and stability metrics actually move together. They're not trade-offs. You improve one, the other improves. So it feels obvious when you put it here, but it's not intuitive. So, okay, I'm enough fanboying over Deming's. John Willis has an amazing lightning talk called Deming's to DevOps. He starts as far back as Darwin, so it's fantastic. I highly recommend watching that. Oh, and so this is the mental model. It's definitely not correct, right? Ideas don't evolve that way. They evolve in a complex mesh, many other influences, many competing ideas, and they result in the options in front of us today. But models don't have to be correct, they just have to be useful. And for us, this is a useful enough model to use today. Okay, so now that we know our history, the question becomes, where do we go from here? And we'll try to use Deming's sort of lessons to use as a lens to apply to what might be a good developer productivity initiative versus what might not be a great developer product. And to be honest, it could be anything. We could use TPS, we could use Lean, we could use the principle of DevOps as that lens, because the underlying principles are fairly consistent. So Deming spoke about, towards the later part of his career, he sort of consolidated his findings in one of his books, and he called it the system of profound knowledge. Uh, it sounds very abstract, but we'll go over it one by one. And there's 4 aspects to this system. But the key part, it is one system. You can't separate the parts from the whole. You take one away and it stops being the same thing. So let's start with the first one, the central one, appreciation for the system. Appreciation for the system is basically Deming's way of saying that we need to view our organizations as a system of producing value and be able to have a model of how that value is produced, how it reaches the customer, how customers interact with the value, and what feedback loops affect the whole thing. Where are the bottlenecks and where are the points of leverage? Because the points of leverage is where you can make productivity interventions. Now, I've been trying to talk about this for a while and not very successfully, so I've come upon a new idea, which is try to use computer-based modeling to try to actually demonstrate how systems sort of behave. So I hope it works. So I'll just jump to this. Now, this is a computer-based model. It's something called an agent-based model. And this might be new to a lot of us. It's new to me as well. But pay attention because there will be a quiz and I'll pick somebody at random to answer a question. So I'm just going to start it off. It's slow it down so it gives me time, right? So it's basically what you see here, these 10 green dots. These is a team of 10 developers, right? They're sitting in these 2 rows in an office of 5 neatly, and they're delivering a project of a certain scope. Now, when the dots are green, it means that the developers are doing work that they plan to do. But if I speed the model up, you can see that sometimes dots turn red. Dots turn red when developers find complexity or unplanned work or problems or bugs that they must solve before they can go back to delivering planned work. And what you'll see in this graph, this tiny blue line over here is the amount of work finished. And when it reaches the top of this line is when we've finished delivering the project. So I'll let this model run in the background for a while. I'll just give you a couple of more data points. And just pay attention to the only things I'm talking about because it can feel a bit complex. So this is a state diagram that describes the behavior of each developer. A developer can basically be in a no problem state where they're just doing planned work according to a rate. Now, at a rate of 10%, any developer a probability of 10% any developer can discover some unknown work, which means, things you didn't plan for, bugs that show up, complexities you didn't estimate for, other things. And they basically, the amount of time it takes to solve that unplanned work is basically a probability distribution, which depends on how much know-how or knowledge that developer has. So what happens is the more the knowledge I have, the faster I solve this problem. And the other thing is every time I solve the problem, a new problem, I gain some more knowledge. So if I speed my model up, what you see is that it takes about 150 days. If you can't read it, I'll read it out. 150 days to deliver a project with 10 developers. We spend about 308 man days in unknown work or problems. So basically, that's about for 10 developers, 150 days each. It means that we spend about 20% of our time solving for unknowns, which is a reasonable estimate, right? Projects, in my experience, have way more time spent dealing with the unknowns than just 20%. And what you'll also see is that this is the time taken to solve each unknown. You'll see as the project goes on, the developers gain more knowledge, they figure things out, and the impact of those problems drops away. And this also sort of resonates because early on in a project there's more flux, you're norming, storming, and then you've not discovered a bunch of things. So early on there's more flux, and later on there's more stability. So I can solve I can deliver this project in 150 days with this strategy. And now there's one more strategy up my sleeve, which is if I stop the model and I basically instruct the developers every time you run into an unknown, ask for help. And if I run this model, what happens is every time a developer turns red, they ask for help, and somebody who's in a green state will go over to their desk, pair with them until they solve the problem, and then go back to their desk. Now, problems get solved slightly faster because there's two people pairing on them, and both of these people get the boost in knowledge. So the next problem is easier to solve for both these people. So it's basically what you might see in a team where somebody says, oh, I'm stuck in a stand-up. Somebody else says, okay, let me come over and help you solve this, even though I have my work pending. Now, if I speed this guy up, let me try to restart the model. The gods are not kind today. Okay. Yeah, this is probably my computer being slow. So if I speed this model up, you see that I deliver in something around 135, 38 days. So I'm like 10 to 15 days faster than my other strategy. So I'll pause here. So far, so good. It's a bit new. I know it's a bit, but okay. Does anybody want to volunteer a lesson they learned from how to deliver a project faster from this? What is like a takeaway? Sorry? Okay, yeah, that's a pretty good one. Ask for help. Yeah, fantastic. Anything else? Okay. Okay, that's a stressful part done. Now I know my demo is not going to crash. So now if I try to look at my things that are affecting productivity or how fast I delivered this project, there's a work rate with everybody's working at a certain rate of planned work. Unknowns show up. They have a negative impact on productivity. But every time unknowns show up and I solve them, that increases my know-how. I solve unknowns faster next time. So increasing know-how has a positive impact on productivity. When I pair on a problem, I affect productivity negatively because when somebody leaves their desk in the green state, there's less people in a green state writing, doing planned work. So at least for a while, your velocity will dip. But then, because both of us solve the problem faster and I know how doubles, eventually my productivity goes up because I deal with the unknowns a lot better. I think one thing I forgot to point out in this run is that the total time spent in solving problems for the team was 222 days as opposed to 300 odd days. So like 30% lesser. Okay, so now what's a common intervention that management and I'll call myself management, make to make teams go faster? We say, okay, everybody must go as fast as possible. You have velocity targets and you all must deliver this in this time. So you've heard this before, right? Or like, I'm not the only person cursed with this. Okay, so what happens when I do this in an attempt to increase my velocity? If in this case I ask for help, a developer is going to ask for help, but somebody is way less likely to offer me help because they're worried about their own targets, because they have to sacrifice their targets to help me out for the better good of the whole system. If I try to individually optimize the parts, I sub-optimize the system. Right, that's I can end my talk here. And actually now I have no idea. So even if they cut me off short, I'm really happy that we made it to this point. Now let's go back to defining a system. There's a few definitions. Russell Eckhoff said it's more than the sum of its parts, it's the product of its interactions. So the value in a system is coming from the interactions, not from the individuals. Peter Senge took it a step further. He built a definition of a system where there are no parts. So it forces you to think purely in interaction. That's quite awesome. And Deming used to use this equation. I don't know what the proof is, but he basically said if X is my contribution and Y is the system's contribution, the total contribution is my contribution, the system's contribution, and my interaction with the system's contribution. What he was trying to say is that you cannot isolate X. You just can't. It's impossible to know how, like, what a single person's contribution to a whole system is. Okay, some points about when trying to sort of catch yourself when you're trying to do these developer productivity initiatives, right? The last one over there, blaming individuals. I've heard people say, our developers aren't good enough, right? Every time you hear say our developers aren't good enough, you can imagine somebody is finding faults in the wrong place. All developers should have individual targets. Okay, this is good. I was trying to come up with what should developers do, right? If you feel powerless as an individual, if everything is a system. So Peter Senge has an answer for this in his book. He talks about personal mastery. So responsibility of me as a developer is to relentlessly improve every day at my job. That's my responsibility. And if I'm doing that, I'm thinking as a system. Okay. Knowledge of psychology, this is important because organizations are complex systems. They're complex human systems. To figure out how they behave, you need to know how humans behave. And so Deming had these 14 points for management, and few that were very directly relevant to psychology is 8, which is drive out fear, and 12, which was about motivation. So we can talk about fear first. So this is our system right now. And let's talk about what makes this asking for help strategy work. Any guesses? The likelihood that I will ask for help. What determines the likelihood that I ask for help? Yes, 110 marks. Safe, there's a pattern of behavior where I'm ridiculed, shamed, or ignored, or looked at as a problem if I ask for help, I'm not going to ask for help. So psychological safety gets like bucketed sometimes in the woo-woo well-being bucket, but we can model that in that system as a probability of asking for help. And if it's 0, your system will underperform by 12 hard man days. I don't know how much money that is. But so there's like a direct impact to your bottom line. It's been proven by research papers out of MIT that modeled what happens when you have a pathological organization where the culture is shoot the messenger and don't come to me with problems, come to me with solutions. In that project over there, the project missed the deadline by 100%, and they modeled that at 50% safety. I'm sort of paraphrasing here. And over there, that one missed the deadline by about 200%. They modeled that like nobody's ever reporting any problems. Okay, so I want to create a really visceral image to help explain to people why safety and fear matters. Is because organizations are like groups of people, and the structure that connects them is like information flows. Once you have fear in an organization, information will stop flowing. And this is also how my doctor spoke to me about not eating fried chicken. So it's quite powerful. I haven't had one in a while. Okay, so there's this model of measuring safety and organizational culture. And so you don't need to read the whole thing, but the thing just means it's measurable. So your system of productivity and experience probably should be measuring this. And as a consultant, my dream is to have a model named after myself. So I've improved it to the new Wallstrom model. And these are dysfunctions that I've seen. Like I've had some lucky experiences observing many of different types of these organizations. And this is things that I've seen as an impact of that. There's one worth calling out where small firewall rules unblock port 80 requires CIO approval. That's just, everybody's super busy, everybody's swamped, everybody's working weekends, but nothing's getting done. That's what these organizations look like. Okay, what about motivation? So Deming said, remove the barriers to motivation. Help people find pride in their work. So the job of management is not to motivate employees. The job of management is to not demotivate employees. Google had this study about, oh no, this is from Microsoft. Again, this paper called Today Was a Good Day. So they did some surveys and interviews and surveys, and they figured out, okay, how do developers define good days? So it turns out developers actually want to do work. They don't want to slack off. They want to create value in projects they find meaningful, and they don't want to waste their time. So that brings us to think about how are you thinking about your tool that's going to measure all developers and all teams and build that dashboard and report it to you. Are you thinking, what's your underlying assumption of command and control, that I need to see who the low performers are and root them out? Or is your underlying assumption that I want to find out what the bottleneck is and help people do better at their jobs? And that's something called Panopticon. Now ex-colleague of mine introduced that to me. It's basically a way to design a prism where you can see all cells from one central location. And it's a brilliant way to design a prism because the underlying assumption in a prism is that everybody wants to escape, right? Nobody wants to be there. But is that the underlying assumption of your organization? Knowledge of variation. Now, this is like, this is interesting. So Deming had a mentor. I can slow down now. I just checked the time. Deming had a mentor called Schuhart, who Deming worked with in a factory in the States before he moved to Japan. And they basically came up with a game-changing way of doing quality improvement. And it was basically something called statistical process control, where they would chart variation on a control chart. And the takeaways from this is basically, variation is normal in a system. If I have a dashboard with a line, it's going to go up and down. Most of that variation is from the system, not individuals doing something weird on Thursday, so that line is dipped or something like that. Most of the variation is part of the system. So it stands to reason, if you want to minimize variation, we need to make improvements in the system, not in the individuals. So Deming had estimate of how much variation is coming from the systemic causes. And he said it's about, he called it common cause variation, he said about 94%. And special causes, which are like idiosyncratic causes, one-off events, individual bad actors, is around 6%. So the problem happens in the misunderstanding of variation, is when we think that a common cause, normal variation, is actually special cause. And you may see, these are some of the symptoms. Some I've seen, some are obvious, of where we as management, we might react to try to help the system, help improve our organization, react to common cause variation with special cause thinking. We're like, okay, we do a semi-annual midnight deployment. Somebody did a misoperation. They didn't follow the procedure. They missed step 13, fire them, right? So people know there's accountability. Now, if I'm doing deployments twice a year and at midnight, most people are going to make mistakes over time. So is the problem with the person, or is the problem with how the system is set up? And then there's like, okay, my CIO said my velocity for this team was too low. Management goes in panic mode, they overreact, they try a bunch of things, usually make things worse. Okay, I'll try to go over an example that I've seen before. This is sort of adapted from real world experience. We were team, few of us delivering this project. I target this as points per iteration, so it's a velocity charted as a control chart. And you see that we are underperforming the target of 10 early on. And then we have a massive dip in iteration 4 to 4. And then something happens and we do a lot better. So how we, and I'll include myself, how we sort of reacted. First, we didn't have this chart. We used to have the burn-up chart. Burn-up charts are not very useful because you can't see the trend in velocity as obviously as this, right? What's my mean and how much is the variation? So first, we ignored this trend. There's an obvious trend here, right? A control chart will show you a trend if you're consistently. So why is this happening? There's something about it that we are consistently at one number for 3-4 iterations and under our target or under the mean. And then something happens over there. We have a dip and then we overreact. And once we overreact, we try a bunch of things and some of them work, but we don't know at what cost. Our velocity starts hitting 15 and 17 and we celebrate the hell out of it, right? We pat the developers on the back, good job, well done. Now we did a little bit of digging after the fact and we got estimates for developers about what do you think would have happened if we did absolutely nothing. The consensus estimate was that that would be the velocity graph if we had done absolutely nothing. One of the things that was possibly happening is every 3-4 iteration, things pile up at the QA lane. And that sorts itself out in every 3-4 iterations. So the consensus was we would have made that green line happen, meta targets be in line without any weird interventions or any costs associated with those interventions. I'll go into the costs in a little bit, but the problem with one of the problems that can surface here is when you celebrate that without knowing why there is that behavior happening, like are people working overtime? Are people taking shortcuts? Is my tech debt piling up? I've just celebrated something, so I'm trying to reward a behavior without knowing what behavior I'm rewarding. And the other thing is when my velocity dips below a peak, I'm demonizing it. Why are we so slow? If we can hit 15, why aren't we doing 15? And that demonization results in people persistently feeling the need to work overtime. And one of the common system archetypes a common system archetype is something called shifting the burden. The only thing you really need to understand here is that instead of solving a root problem in the system, you apply some special case to try to mitigate the symptoms of the problem, and you don't solve the root cause. So caffeine addiction is pretty good. Instead of my energy levels are low, instead of sleeping more and going for a run, I just drink 6 coffees a day. That's a true story. So in organizations, this ends up being something called firefighting and heroics. Is that once you get addicted to heroics and firefighting and somebody pulling an all-nighter and somebody working on Saturdays to get stuff done, that's an addictive behavior. People don't feel rewarded, people don't feel acknowledged until they behave like this, so nothing gets done without these heroics. Okay, just looping back to other misunderstandings or variations, give you another second to have a look. Okay, finally, theory of knowledge, or how Deming put it, how do we know what we know? And for developer productivity initiatives, is like, if I'm making changes in the system, I'm twisting these knobs and dials and trying to adjust things, what works? And how do I know what works? And how do I know what direction the system's going to go in? So Deming, this is probably familiar to a few people. Plan, do, study, act. Some people call it check, act. Yeah. So Deming used to call it check, act, and he got sick of saying check because he thought it sounded like inspection. And he was against inspection, so he changed it to study. This is also a cycle inspired by his mentor. He adapted it when he brought it over to Japan. So one way to explain this is that when you're trying to make interventions in a system, you have to do it in a systematic way, which is like you have to have an hypothesis, you make one change, you study what the results are, and then you decide, okay, do I proceed with this? Do I crank this knob up a little bit more, or do I just let it be? Kent Beck, I was on LinkedIn in the morning, and Kent Beck had a post about make predictions. He's talking about TDDs, like when you run your test on your local machine, make a prediction whether the test will fail or pass. And the reason is when you make that prediction, your mind goes into a different learning mode. You're not just turning a thing and seeing what will happen. You're actually making a hypothesis in your head. So making changes without making a prediction, you're not going to learn much. The other thing about this is that success won't look like this. You don't know. Every organization is different. Every organization is a complex system. And the nature of complex system is you don't know how they will behave. So you have to experiment your way to success. So you have to do these plan, do, study, act cycle enough times to figure out, okay, these particular knobs in these particular circumstances give me the result I want. So let's go back here and talk about another really common pattern that you see. And we did. So we did many interventions, but early on we did nothing. We ignored the trend. We don't know why this is happening either. Then we go into panic mode because we have to report velocity at a governance forum, and the top boss is going to look at this number and ask us questions. So we go into panic mode, and we try everything. We say, okay, let's try, like 4 people try 4 different initiatives. So things happen, but then again, we celebrate it, but we don't know what worked. We don't know which one of our turning of the dials was successful and which one wasn't. And John Sterman, who's a system dynamics professor at MIT, talks about this pattern repeating over and over again, which is one of the plausible explanations is early on, when you're investing, when you're starting a greenfield project, you're going to have a phase of making complex early decisions, spreading context in the team, um, figuring out things you didn't plan for, and you'll probably go a little bit slower because you're investing in quality and setting things up right. That variation could just be systemic variation. It could just be a pileup at a QA. But what happens is management or people go into panic mode. They go to the developers and they give them this either beautiful pep talk of why they need the developers to step up, or like a fear-driven monologue of, I need you to step up, and there might be threats of things. None of that works. But because the team had been investing in quality, and that's just normal variation, the graph goes up on its own. But the lesson that we have learned as managers is that my pep talk and my fear-driven monologue is what got the team to shape up. And that's why, despite fear not working, it remains like one of like the most common sort of arsenal in people's toolkit. Like, I'll just go give team a pep talk. Have you received a pep talk from a manager? Has it worked? Rest my case. These are the things, interventions we tried. I do not have time to discuss them, but I thought I'll share them with you and let you think about. The last one you can ignore because that's the systemic variation. We knew the thing would go up on its own. These are the interventions we did. I mean, homework. Think about it. We can discuss it at lunch. But it's interesting. Applying this to PDCA is, okay, I'm going to have two stand-ups, one in the morning, one in the evening. I'm going to increase supervision of developers. I expect this to increase the velocity. I'm trying to do a hypothesis here. Did it work? Did it not work? One, I'll only find out if I do this in isolation. And two, I have to have an hypothesis and I have to measure a few things. Am I measuring velocity? Am I measuring quality? Are people taking shortcuts? Am I measuring tech debt? Is it piling up? Or are people hiding shortcuts? Am I measuring team health? Are people working overtime to make this happen? How is my action affecting the system? Some more points about when you're thinking in systems, when not, when applied to PDCA. Like, let's just adopt the Spotify model. Let's just do what our competitor is doing. You don't know how your system will behave. You need to experiment. You can't copy other people's system. I need to give developers a pep talk. All right, in time. 4 takeaways, mapping back to Deming's 4 points. Improve the whole. Don't worry about one part of the system. If you optimize one part, you're quite likely to sub-optimize the system. Identify bottlenecks and points of leverage, right? Identify the waste in the system. Avoid a culture of fear and surveillance with your metrics and your dashboards. Understand and tolerate variation. Don't overreact. And this is probably the hardest. This is the one that scares me the most, right? Management. I put like a whole dashboard full of metrics that tells the whole story of an org, and there's variation happening, and people don't have an appreciation for variation. Now, suddenly, the opportunity for us to make bad decisions is a lot more. And experiment your way to success. All right. I have 3 more minutes for questions, but thank you very much. It's my LinkedIn. That's my role. Thank you.